This is question 3 of the tutorial Signals and Systems. In this question, we are asked to find the discrete time Fourier transform of this sequence h of n. And here n goes from 0 to infinity because of this step function u of n. So it looks like this, time 0, and before time 0, the values of h of n is all 0, and at here this is half to the power of 0 is 1, and then second one is half because half to the power 1, third one is half to the power of 2 is 1/4, and so on. So although it becomes very, very small, it never becomes 0. So h of n is an infinite sequence. It's an infinite geometric sequence. Now, so when we have this sequence and we want to take the DTFT of this sequence, we have to apply this formula. This formula explicitly says that we need n equals to minus infinity to infinity. But since we are using only a causal signal, the bottom side or the left hand side will start from n equals to 0 and it progress to infinity. Therefore, technically, we cannot do this by computation because we have to sum an infinite sequence. Alright, anyway, let's see what we can do. So in A levels, you have studied this. This is a geometric series. A geometric series is the sum of a geometric sequence, infinite sum of a geometric sequence. So let's put our DTFT equation here. We put our sequence here, and to take the DTFT, each values of the sequence is multiplied by e minus j omega n, capital omega. Now we can collect. First, let's get rid of u of n. So it means that we start from n equals to 0 to infinity. We then recognize that these terms are common. We can collapse the common terms at the bottom. So we collect this. And this is half e minus j omega. So this guy is actually a complex number in the complex exponential form with amplitude half. So its value is half. And it has a different angle based on omega. Anyway, because the absolute value is less than 1, we can apply the geometric series formula. You'll realize that if the value of r is less than 1, it will converge into this equation over here. Okay, the proof, please read it by yourself. We assume that you will be able to do this by yourself. So ultimately it's 1 over 1 minus r in our example, and r is this term, so we get this formula over here. So h of omega is a function of omega from, we can do it from 0 to 2 pi for a single-sided spectra, or for minus pi to pi, a double-sided spectra. It's totally up to you. Okay, so in our example, we are going to plot minus pi to pi because it looks nicer. Alright, so let's copy down our formula, and let's have minus pi to pi. This is normalized to pi, so it's minus 1 times pi, and here's 1 times pi. So this is positive pi. So we plot the magnitude and we plot the angle. So what you should do is that you write a Python program or a MATLAB program and plug in this equation, and you vary this value, and out will come a complex number, a plus jb. To get the magnitude, you just take the magnitude of this, and to take the angle, it is the inverse tangent of this complex number. Right, so this is the value of the magnitude, and this is the value of the phase. Now I'm show you the equations. So in MATLAB, we define w from minus pi to pi instead of 0.05. the h of w, the discrete time Fourier transform, is 1 over 1 minus half exponential minus j times capital W, which is this. That's it. Once you have executed this equation, we have the DTFT of Hn. And then to plot, we use this. So we wanted the horizontal axis to be with respect to pi, so that's why we divided by pi here. So that's why you get from -1 to 1. To get the magnitude, we just use absolute. Absolute of a complex number will give you the magnitude. And then we will plot also the phase. Here we don't care about whether magnitude is small or large, so we want to plot for all angle of HW. That's it. So 211 is a top plot, 212 is a bottom plot that we have seen over here. Now, you'll be wondering, can I do it computationally? Right, so I will plot the theoretical one for you, which is in black. You can see it over here. I can use length of 2, that means h of n. Although it is infinite sequence, I can choose 2 values. I can choose 5 values, n equals to 2, n equals to 5, and I can choose n equals to 20. So basically I generate a sequence and I take the Fourier transform of this sequence. Now you'll see that when n equals to 2, it is that red thing over here. But by the time when it is n equals to 5, it is quite close. And when it's n equals to 20, 20 and the theoretical one is almost identical. So you'll see that actually, even though this is an infinite sequence, once we use, in this example, up to 20 numbers representing Hn, it is enough. So you'll see the code to do it here. First is I choose the 3 values, 2 samples, 5 samples and 20 samples, and then I basically take the values here to generate, let's say 0.5, 2 sequence, 5 sequence or 20 sequence, and then I just take the Fourier transform with respect to n equals to 100. So even though, let's say I have 2 numbers, I'm padding 2 numbers with all the zeros after that, so that the Fourier transform is operating at capital N equals to 100. And then after that, I plot the different, the different DFT of the finite sequence. So the take-home message is this. The take-home message is that in a sequence that is infinite, and the only infinite sequence we are going to play with is the geometric series as well as the pure sinusoids. Okay, and the step functions. And once we have this infinite sequence, we take the Fourier transform. It looks like this. We can also use a finite length of the infinite sequence and take approximation of it. So the longer we take, the better it is to approximate the real value. That's the take-home message. The code is here. You can take a look and you can try it by yourself. With that, thank you.